This could be a difficult process. This could go unstable. In fact, it has gone unstable, you see. This is called Puzzling Plastics, and it's a great project because it links up chemists and physicists and mathematicians and engineers and industrial scientists, all focused on one task of trying to do with our polymer materials, the humble materials that make plastic bags, but also the materials that are making body implants, high-performance sporting goods, to do with those materials what nature does, where every molecule is placed in such a way that it's best for the material and maximizes the performance. So we're trying to learn ways of making plastic materials by placing the molecules just where they need to be.
So here we're comparing the experiments with our known polymers.
Experimentally, there has been extraordinary advances in ways of looking inside matter using neutrons, nature's neutral particles, to scatter and feel their way right inside the structures of molecular matter. Theoretically, there was a revolution in the 70s, a Japanese-British collaboration, Masao Doi and a man called Professor Sam Edwards in this country, produced a theory, a very simple theory, but a very powerful theory, of how entangled polymer chain molecules flow. And they likened it a little bit to microscopic spaghetti. Imagine a bowl of spaghetti moving around. If you want to eat spaghetti, the polite way of doing it is to wind it up on the end of your fork. And what that's doing is making each strand of spaghetti just wiggle along its own length. And they reasoned that perhaps this is what was happening in a polymer fluid. Very simple idea. Turn it into mathematics, turns out to be immensely powerful. 20, 30 years later, we're now using that theory to be able to design new polymer materials at the molecular level and then predict how they will flow, what sort of products they'll make in a factory.